Hello there, wonderful people. The objective for me in this video is to show that this characteristic equation for eigenvalues is true. Just a quick note on notation. For when I write out a symbol for a matrix, I tend to use a little tilde, right? So if I put a tilde on top of an A, that means I'm referring to a matrix that I'm calling A, okay? So let's go ahead and start by talking about eigenvalues and eigenvectors, right? So the definition, so this is definition of an eigenvector is that if I have a matrix A and I operate it on an eigenvector V, okay, right? And we know that very generally, if I took any matrix and I acted it on some vector, it's going to transform the vector, right? So I'll go ahead and make just very quickly here, let's make a little compare and contrast. So this is for any vector, and I'll call this u since I'm using v to denote an eigenvector. Right, so if this here is u, and it's in 3D space, so maybe this is the projection of u onto the xy plane. So here's u, and now I go ahead and I transform it with a, right? A could rotate it, it can scale it, it can do a whole bunch of things, right? And it transforms u somehow. And so this is A on u, right? And it just outputs another vector that's been transformed. Now, an eigenvector, if I operate it on v, basically we're requiring for an eigenvector that there's not going to be any rotation, that A acting on V is equivalent to some scalar factor lambda scaling V up or down, right? So again, like very graphically, and I'm not being very rigorous about these pictures here. I'm just trying to get the main point across. Right? So here we go. Here is now V. Here's X, here's Y, here's Z, and I go and I apply this transformation on V, and V doesn't rotate at all. It simply gets scaled up, right? It gets scaled up. It hasn't been rotated, and of course this has some scalar factor with which V has been scaled up, which is lambda. Right, so lambda is this scalar factor, which is the eigenvalue. So if we're good on that, what we can do from here, just from this basic definition, is I'm just going to go ahead real quick. I'm going to move lambda v to the other side, okay? So we have AV minus lambda v is equal to 0. And we also know that the identity matrix acting on V, by definition of the identity matrix, it's just going to give us V again. So I can rewrite this equation again as AV minus lambda times IV. Still feeling good about that. And this, of course, equals 0. And now, this is really nice because I can take out A, lambda, and I, right? A minus lambda I, and all of this is going to act on V. And this is going to be equal to 0. Now, this is starting to look like the characteristic equation, right? Just as a reminder, what we're trying to prove is that the determinant of A minus lambda I is equal to 0. So this is a good start. We're not yet sure how this is going to relate to a determinant, but we have something in this tempting form where we have this a minus lambda I kind of isolated in its own little world. So the next thing I want to talk about is invertibility of a matrix, just as a quick refresher. So, and for this little aside, I'm going to choose a new symbol for the matrix that I'm talking about. How about let's choose chi, okay? So this is just an aside. I'm just talking about this chi very generally. If chi has an inverse, or if chi is invertible, those are two ways of saying the same thing, right? And we denote this as chi inverse, right? This is defined as, if I take chi and I multiply it by chi inverse, this is defined to give me the identity matrix, right? Just like how if I took two scalars, right? If I took a and then I multiplied it by 1 over a, this would give me 1, right? A inverse equals 1. Chi inverse gives me the identity matrix. Now the thing is, if I take the determinant on both sides of this equation, determinant of chi inverse equals the determinant of I, right? What's the determinant of the identity matrix? Well, this is just 1, right? And again, confirm yourself. I'll do it really, really quickly just for a 2 by 2 matrix. So if I take determinant of a 2 by 2 identity matrix 1, 1, 0, 0, just to make sure we're on the same page, right? We multiply these, subtract the multiplication of these. This equals 1 minus 0, which equals 1. Okay? So nothing esoteric, nothing complicated about that. The other important thing to note is that we can take this determinant and we can distribute it over chi and chi inverse. And again, this is another property of determinants that I don't think is too difficult to understand. We could just very easily test this assertion. Right, and so we've just manipulated this slightly. We've just manipulated this above statement slightly. And so both of these we can consider conditions for invertible matrix chi. Okay? So if chi fails this bottom condition here, it must not be an invertible matrix. Okay? So I'm going to call this condition alpha. If chi fails alpha, it cannot be invertible. Well, let me ask you real quick. When does chi fail this condition alpha? Well, it's very simple. If the determinant of chi is equal to 0, then obviously 0 times anything is still 0, and we get 0 is equal to 1, which we know is not true. So from this, we can immediately conclude if the determinant of chi is equal to 0, it fails condition alpha, right? Again, condition alpha. What's up here? I'll zoom out so we can make sure that we can see our condition alpha. If the determinant of chi equals 0, then it fails condition alpha, and chi is not invertible. Okay? So I hope we feel really good about this condition. So any matrix with a determinant of 0 does not have an inverse. It's not invertible. Okay? So now let's go ahead and, so let's return back to the equation that we had before. So we had A minus lambda I acting on V is equal to 0. So this was our condition for an eigenvector V with eigenvalues lambda. Real quick, just to make this next part of the discussion easier, I'm going to group this. We have just a matrix minus a scalar times a matrix. This is just going to output another matrix. And I'm going to call this matrix gamma. Okay. So in other words, I can rewrite this above statement as gamma V is equal to 0. Now when we write the equation like this, what I can see immediately is that gamma cannot be invertible. It can't be invertible because if gamma had an inverse, if gamma had an inverse, I could take this equation up here, multiply both sides by gamma inverse, and I would ultimately get gamma inverse times gamma is the identity matrix I, and gamma inverse acting on the 0 vector is just the 0 vector. And so I would get that V is equal to the 0 vector. And this is a very trivial result. Any matrix operating on the 0 vector is still going to output the 0 vector, right? Which I guess you could say is scaled by some amount because anything times 0 is still 0. So because I can do this for any gamma that has an inverse, right? And basically reduce this down into this bottom statement here where my only eigenvector is the 0 vector, we conclude from this we conclude the only gamma with non-trivial eigenvectors is one that is not invertible. Or based on the condition we talked about before, right? A matrix is not invertible if its determinant is equal to 0. And of course here we have that gamma we defined as A minus lambda I. And so we get that determinant of A minus lambda I must be equal to 0. And this here is the characteristic equation. And it's extremely powerful. So we use this characteristic equation all the time, but it's super duper important to know where it comes from. This is a really important constraint that helps us solve for our eigenvalues lambda. But hopefully this video was helpful. Thank you so much for watching.